So the core of this class is going to begin exactly at power series, right? So we'll take power series, we'll take the ordinary points, then we'll take the singular points, that's where we'll get to Frobenius method. And then from there, we'll go to special functions. So we'll talk about the gamma function, the beta function, and if we still have time, we'll talk about the polynomials, right? So that's what we are looking at. Of course, I think we have one more, a topic before it. That's the Green's theorem and Sturm-Liouville. Maybe I'll leave that one to David to sort out. Now he saying you understand that. Make it send material to us. So, first off, I'm sure everybody can hear me, Abi. Oh yeah, now. So the power series solution is a method of solution at the ordinary point. Yeah, while the Frobenius method is a method of solution at the singular point, right? So when we get to the Frobenius method, we'll talk about the singular point, as well as what makes it regular and what makes it an irregular singular point and all those ones. But first, let's talk about the ordinary point. We'll pick out some basic definitions. Remember, if you have, let's just write a random ODE, b naught of x y prime prime plus b1x y prime plus b2x y, let's say, is equal to f of x, for instance. Let's just put f of x there. Remember, every single time we carry out power series, to test whether a function is ordinary point or singular point or whatever, our goal is always on, yeah, the camera is far from the board. Now, you can zoom the board though. Is it clearer? Because I'm using a camera resolution, so I know it will be clear if you zoom in. It's okay now, Abi. Okay, so let's continue. Right, as I was saying, I said the biggest test that we have to know whether a value or a point will be an ordinary point or a singular point comes from the coefficient of y prime, right? So let's go ahead to divide. If we divide, we'll have something like this. Abi? Now, you say that x naught is ordinary if by the time you put x as x naught in this denominator, remember that b naught is now the denominator of all of them, Abi? So the moment you now put x naught into that denominator, that means whenever x is equal to x naught, b naught of x naught now is not 0, which means whenever you put that value here, you will get a result that is not 0, which means this place will not be undefined. However, x naught will be singular if b naught of x naught is equal to 0. So that's just the basic difference between an ordinary point and a singular point. The ordinary point, when you put it into that value, you won't have 0. But if it is a singular point, when you put in that value, you would have 0. So now our power series solution is for this point, which is when it is ordinary. That is the very first thing we are going to solve. So how do we solve that? Let's see it together. Who they enter? Okay. Now let's continue. Let's pick an example. and then we'll see how the process goes. I hope we don't pick an example that is too long. So to save our time, we'll be using one example that is explanatory, right, to showcase the process. So I will explain that example as much as we can. If you have questions, you can ask them within that example too, because we won't be taking a second example. So we'll be using that example to clarify anything we want to have. Solve. So let's start this. Now, before we start this, let's give ourselves a very quick note. Remember, what is the standard form of the power series solution? That is the most important thing. What is that standard we use? We say y is equal to the summation. So sometimes we use k starting from 0 to infinity ak x is per k. Abi? This is the standard power series solution. You can use k, you can use n, whatever value you decide to use is fine. Now, what makes it unique? What makes this solution unique? In fact, the full form of the power series solution is in fact y is equal to summation k starting from 0 to infinity ak x minus x naught raised to power k. This is the standard form. That is, x is equal to x naught is an ordinary point. So when we use this form, what does that mean? It simply just tells us that at this point, we are considering x is equal to 0 to be the ordinary point. That is just what it means. So basically, or usually, we are always solving power series solution where we are using x equal to 0 as our default ordinary point. However, it does not mean that x equal to 0 is the only value that can satisfy it. The condition is simple. So long as that value is such that if you put it in the coefficient of y prime prime, you will not get 0. Then that point is an ordinary point. Are we together? So for instance, here now, they just said solve this. There was no mention of where we are going to solve it, whether it's at ordinary point or whether it's at 0 or any other point, right? But we are going to solve it straightforward as if we are solving at x equal to 0, because that is the default power series setting, right? And you can test x equal to 0 is of course an ordinary point, because if you put x equal to 0 here, you are going to get 1 as a result, right? So it is a value that is not 0, so it can be an ordinary point. However, you would also notice that it is not only 0 that will satisfy that condition. If you put 1 inside here, it will be satisfied. You get 2 as your answer. If you put 5 here, you would also satisfy your condition as an ordinary point. You get 26. So it means that there can be so many points that can be ordinary points, and that's why we have this general formula, which is very, very important for us to note, right? So let's just keep that in mind. Okay. Now, another thing we should also keep in mind is the fact that, now let's consider this one. Let's target equation 1 or something. This one now, remember, how do we evaluate using the power series or with any other series solution in the first place? Our goal is anywhere we see y or the differentials of y, we replace it with the power series solution. So let y be equal to summation k starting from 0 to infinity. Remember, it doesn't always have to be k. You can use something else if you like. ak x is per k. This will substitute for y, no problem. But we have y prime, we have y prime prime, right? So we differentiate y prime. Now, how do we differentiate it? And how would this differential affect the counter? This is the most important thing. Remember, if I write this out as a series, it's the same thing as saying a0 plus a1x plus a2x squared and so on. We agree. Now, if I differentiate this function, what happens? A naught is a constant, so it becomes 0. This will become A1 plus 2A2x plus 3A3x squared, and so on and so forth. What does that mean? It means that the first value will vanish, because when you differentiate the constant, you have 0. The same thing will apply to the counter. The counter will now become summation k starting from 1 to infinity k a k x raised to the power k minus 1. And if you translate this, what would you have? You would have a1 plus, so let's just quickly write it, a1 plus 2a2x plus, and so on and so forth. Are we together? This we have gotten from the differential of the first one. To get y prime prime, which we need here, we differentiate again. This time, a1 is now the constant, so it will vanish. You are now starting from 2. Abi, differentiate this function. What do you have? K minus 1, akx, k minus 2. Abi? And if we were to look at it here, what would you have? 2a2 plus whatever comes next. I'm sure this is clear at this point. If it's not clear, please let me know. Okay, let's now continue. The next stage is these three things now. We'll substitute this, this, and this. That's all we need to do. And this is where the major work is. The computation of this method is the work itself. It's not the method. It is the computation that you have to do. So you have to be very careful how you use the sum. You have to be very careful how you operate the counters, and so on and so forth. So let's quickly look at it. I'll have 1 plus x squared. I'll replace that with this one, summation, k starting from 2 to infinity, k minus 1, ak x raised to k minus 2. I'll write everything line by line, so we have clarity. Minus 4x, substitute y prime. That will be k starting from 1 to infinity, k ak x raised to k minus 1. Then plus 6 summation k starting from 0 to infinity, and here now ak x raised to k, and this is equal to 0. We know what this kind of function is called. This is an homogeneous equation because the right hand side is 0, so that's not a problem. Now the very first thing is, let's expand this. Expand how? There's a value of x here. There's a value of x here. We can unify the values of x by law of indices, right? So that's just what we are doing. So 1 times this, so it's normal expansion. It's just like if you have 1 plus x squared y is 1 times y plus x squared times y. That's exactly what we want to do here. So what would this give us? 1 times all this sum. That would simply be summation k starting from 2 to infinity, k minus 1, ak x k minus 2, then plus x squared times this. So obviously we know that law of indices will apply, right? Minus 2 plus 2, that's 0. So have summation k starting from 2 to infinity, k minus 1, ak x raised to power k. That's fine, Abi. Next, we come here. We unify this as well. Minus 4 summation k starts from 1 to infinity, k ak x raised to power k. 1 minus 1, that's 0. Then here you have plus 6 summation k starting from 0 to infinity, ak x raised to power k is equal to 0. Are we good? Okay. Now, at this point, we have substituted the value of y prime and y prime prime. We have arrived at this result. This is where we now have to play with the sums. Now, there are 2 rules that you must maintain. How you want to maintain them is your own. But you must always maintain those 2 rules. Number 1, before you even evaluate anything, you must try as much as possible to unify the power. unify the power of the variable. Let me say it completely. You must try as much as possible to unify the power of the variable, which is, there is x raised per k here. There's x raised per k here. Obviously, we know that x is the variable. There's x raised per k here. There's x raised per k here. There is x raised per k here. But there's x raised per k minus 2 here. So at that point, we have to unify x raised per k minus 2 to come in line with x raised per k, which is the other values. First thing. Once you can now achieve that, or once you have achieved that, the next thing that you have to now achieve is to unify the counter, which means bring all the counter values together. Sometimes, and this is a very unique case, sometimes in the process of you unifying the variable, the counters will unify. Sometimes. But in other cases, you might have to unify the variable first and then deal with the counter later. Regardless of whichever one is the case, you will still be able to proceed. Now, first off, let us unify the variable. Now, how do we do that? We have an x raised per k here, which is the ideal. We have x raised per k minus 2 here, which we don't want. So let's deal with this x raised per k minus 2. How do we do it? We will shift the counters. Now, what is the surefire way of doing that? We need k minus 2 to become k. Abi? That's what we need. The question you ask yourself is, if you need the counter here to become k, what do? It means that you have to add 2 to it, Abi. That's what you are doing. Now, everywhere in this function where you see k, add 2 to it. So you have to balance everything completely. So if you add 2 to here, you have k, which is what you are looking for. This place has k as well. You add 2 to it. This place has k as well. You add 2 to it. This place has k as well. You add 2 to it. Now, whatever you have done to the function, you will do the reverse to the sum. Whatever you have done to the function, you will do the reverse to the sum. So you added plus 2 to the function. So to the counter, which is the sum, you will do the reverse, which is you subtract 2. Are we together? If you add 2 to the function, you subtract 2 from the counter. If you subtract 2 from the function, you will add 2 to the counter. That is how you balance the equation. We are adding 2 to this function because we want the power on this x to become k. What it is there is k minus 2. So if we add 2 to it, it will become k minus 2 plus 2. And the final answer will be k. Abi? So remember, this is not the only place k is occurring. So we have to do the same thing we did here to this k, to this k, and to this k. But when we have now finished doing the same thing to it, we will do the reverse to the sum. Are we together? Hey. Oh yeah. What will we now have? Here, this will now be 2 minus 2, Abi. So we'll have 0. It will now be k starts from 0 to infinity. This one will now be k plus 2. This one will now be k plus 2 minus 1, which will be k plus 1. This one will be ak plus 2. This one will be x raised per k minus 2 plus 2. That is x raised per k. Abi? Then every other thing will be repeated. Let's repeat it. Let's not rush. We now have plus summation k starting from 2 to infinity, k minus 1, ak x raised per k, minus 4 summation k starting from 1 to infinity, k ak x raised per k, plus 6 summation k starting from 0 to infinity, ak x raised per k is equal to 0. At this point, are we all together? Okay, if you have comments, say it now. Okay, we have now unified the variable. Let's now deal with the counter. Now, how do you deal with the counter? You bring the counter values towards the biggest counter. You will bring the counter values towards the biggest counter. Now, what is the biggest counter here? 2. So it means this one that has 0, I have to split out terms from it from 0 to 1 to 2. This one that has 1, I have to split out terms from 1 to 2. This one that has 0, I have to split out terms from 0 to 1 to 2. Are we together? Now, how do I split out? Or what do I mean when I say split out? This will now be, this one, when k is equal, I know I want to increase or I want to split out the counter so that this k equal to 0 gets to k equal to 2. I'm not shifting counters anymore. I shift counters when I want to unify the variable. But here, I'm splitting out terms. When k is equal to 0, what happens to this function? This will become 0 plus 2, Abi? That is 2. This one will be 0 plus 1, Abi? That's 1. 2 times 1, 2. This one, 0 plus 2, 8, 2. X is per 0, 1. Are we together? Plus, next time, when k is equal to 1, what happens? 1 plus 2, 3. 1 plus 1, 2. 3 times 2, 6. 1 plus 2, 3. X is per 1, x. Then what will be left? Plus summation k starting from 2 to infinity, k plus 2, k plus 1, ak plus 2, x is per k. Are we together? Tó bá ti ń dojú ẹ sọ o. Plus k starting from 2 to infinity. Now I'm here now. I'm done with this one. I've splitted terms out of it and I've gotten the counter to 2. Now I'm here. This is k equal to 2, so I have no problem with it. Then here I have k equal to 1, so I have to split out one term. When k is equal to 1, what happens? Minus 4 times 1 is minus 4. Then a1, x is per 1, x. Right? And then what will be left? Minus 4 summation k starting from 2 now. K, ak, x is per k. Then I'm here. Plus, when k is equal to 0, 6a naught, because x is per 0 is 1. When k is equal to 1, 6a1x. Then plus 6 summation k starting from 2 to infinity, ak, x is per k. All of it is equal to 0. Are we together? Now, I collect all the loose values. I bring them all together, right? So, I pick the constant, that means the one that I have no variable of x. I will now have 6a naught plus 2a2. Abi? A naught plus 2a2. That is, this and this are gone. Then I have this, and I have this. Right? This one and this one can be multiplied together. Right? I say multiplied. Can be collected together. 6a1x minus 4a1x. That will give me 2a1x plus 6a3x. Right? What would I now have left? I will now have these values left. Now, how do I collect them? All of them have the same sum, so it's not easy for me to bring them all together. They have the same sum. Abi? So, the easiest way I do it, right, is, okay, I've written at this point, I know all of them will have the same sum, so they will enter the same summation. Let me now collect them together in terms of the subscript of A. This one is now AK plus 2. This one is AK. This one is AK. This one is AK. Which means 1, 2, 3 can be combined together. And that one will stand alone. Right? So I will now have a big summation. K starting from 2 to infinity. K plus 2. K plus 1. AK plus 2. Then all the AKs, I'll just simply put plus AK and then I'll multiply. Now, this one will come first. K into K minus 1. Abi, that's this one. This one is minus 4K. This one is what? Plus 6. Are we together? All of them xk. Are we together? I hope it's clear. Right? I hope it's clear. K into K minus 1 minus 4K plus 6. All of them is AK. And therefore the AK plus 2, you have this one. Right? Now, don't forget, that all of them is equal to 0 that is on the right hand side. And the 0 on the right hand side, I can write it as 0 plus 0x plus 0x raised per k. Abi now? That is why we can now say, okay, let's equate it to the right hand side. So if we equate the constant part, what will we have? K. This is the constant part. Let me not use K. Let me just call it constant. This will now be 6a0 plus 2a2 is equal to 0. The x part, that will be what? 2a1 plus 6a3 is equal to 0. Then the x raised per k part, we will now have k plus 2, or k plus 1, k plus 2, anyone is fine. Then all of this. This is ak plus 2 plus, let's see if we can combine all of this together. This is k squared minus k minus 4k plus 6. So that will be k squared minus 5k plus 6. Abi? Can we factorize that? Yes. So we can factorize that simply as k minus 2, k minus 3, ak. And all of this is equal to 0. I hope this is clear. What we simply did here is expand this bracket and then refactorize it. Show ye. Okay, let's continue. So we have this point now. We can now evaluate our functions. Obviously, we know the values that will be our independent variables, which means the values that would record the entire sequence. And once we have gotten those recurrents and we can put them into the power series, then we can say we are done with our solution. Wow. So for the constant part, if I make A2 subject of the formula there, what would I have? I have that A2 will be equal to minus 3A0. Right? From the second equation, what will I have? I would have that A3 is equal to minus 1 over 3A1. Right? So A0 and A1 are obviously the recurring values. From the third equation, I will have that AK plus 2 is equal to what? Minus K minus 2, K minus 3, all divided by K plus 1, K plus 2, AK. Abi? And where would this K value start from? This K values will start from greater than or equal to. Where exactly did they start recurring the values from? The sum that brought this equation started from K equal to 2. So obviously when you pick the counter here, it will also be greater than or equal to 2, which is a very, very important concept. So it means the very first value you can calculate here is A4, followed by A5, A6, and so on and so forth. So we have gotten A2, A3. We can get A4 here. Let's see what happens. A4 would now be equal to what? That means K is equal to 2 at that point. When K is equal to 2, what would I have? 0. Can we see it? When K is equal to 2, this part is 0. 0 times all of this is 0. Divided by anything is 0. So long as whatever is here is not 0, actually. So this entire function regardless of what ak is, because ak now will be a2. So regardless of what a2 is, we have 0. What about a5? That's when k is equal to 3. a5 is also equal to 0. Why? Because when k is equal to 3, it is now this part that will become 0. So what will now happen to a6? When k is equal to 4, a6 will also be equal to 0. Why? Because when k is equal to 4, this place will now be a4, and a4 is 0. So regardless of whatever is happening here, all of this times a4, which is 0, would obviously give us 0. So it means that every single thing I'll be generating from here on is going to be 0, right? Thus, the solution is y is equal to summation k starting from 0 to infinity akx raised power k. That is the very first value we started with. This will now be a0 plus a1x, a0 and a1 are the generators, plus a2x squared plus a3x raised to power 3. And we stop here. Why? Because every other value has become 0. But we know the value of what a3 and a2 is, so we substitute. We now have a0 plus a1x plus or minus 3a0x squared minus 1 over 3 a1 x raised to power 3. And then at this point, you just have to collect like terms in terms of a0 and a1. So a0 into 1 minus 3x squared plus a1 into x minus 1 over 3 x cubed is the final solution for this differential equation. That is how we evaluate or solve the power series. So what exactly have we done? We started with the differential equation. We generated the power series solution for this differential equation. We talked about the fact that this power series solution we generated is in fact the power series solution at origin or at x equal to 0. Then we use this power series solution to generate the differential of y and the second differential of y. Then the next step is to take all these differential and put them into the differential equation in place of y prime prime, y prime, and y. When we do that, the next thing is to expand. The next thing is to now unify the variable. So you unify the power of the variable such that all of them have the same power. So here we unified it up to x raised to power k. After you unify the power, we said that if you want to shift, if you want to talk about the function, if you are adding to the power of the function so that it becomes k, then you do the reverse for the counter. So if you are adding 2 to the power or to this function, you are minus 2 from the function or from the counter itself. So here, anywhere we saw k, we added 2 because adding 2 to this power will give us k, which is what we needed. So anywhere we saw k here, we added 2. And in the reverse, we subtracted 2 from the counter. So we are able to unify the variable. Now, the moment we unify the variable, we need to now unify the counters as well. And we do that by bringing all the counters towards the largest counter value, which in this case is k is equal to 2. In doing that, we are able to split out terms from the others that were lesser than it. So here we are able to split out k equal to 0 and k equal to 1. So we had k equal to 2 and so on left in the summation. Here we did not need to split out anything because we already had k equal to 2. Here we split out k equal to 1 and then we were left with k equal to 2 and the rest. Here we split out k equal to 0 and k equal to 1. Once we are able to do that, we will now collect like terms in terms of the variable. Bring the constants together, bring the coefficient of x together, bring the coefficient of x raised to power k together. And then from there, evaluate the coefficients themselves. So the goal of the power series solution is the evaluation of coefficients, right? Evaluating the coefficients in the power series is what we term as the power series solution, which is what we have gotten. I hope that's clear. Anybody that want to ask question, can ask question now. No. David, how far now? When you go send this kidney to me now, Storm Luffy. Be like, no, David, no hear me. All right, can we continue? Can we continue? Okay. So that is that for the power series. But on a screen blur, I'm not sure say it blur. Sir?
Oh, right. Year 11 and
Year 11.
for
10 and 11.
See,
Question
that
bank.
mock exam. Yes, that mock exam is giving me stress.
What is it?
Oh yeah, it's not counting the questions. Like I will upload, it will not reflect that.
Have
I've
you
done
reloaded
that for
it?
like 5 questions now.
Have you reloaded the page?
I've done everything.
Go and drag OG by the trouser. He's in the office.
I've told you.
What did they say? No go they trust that man. Go meet him. Drag him.
No, men generally, we don't trust them. Please giving me a headache. It's annoying me.
Say you don't. Is it fine now? Is the screen clear now? Sir. Okay. Well, I just said that. Okay, no wala. Oh God. I go do this evening or tomorrow by God's grace. All right, boss. Okay, let's do singular points. Oh yeah. Now let's go to singular points now at this point. Remember, or let's consider that our Fox differential equation we looked at earlier. Let's use 0 this time. Let's make it homogeneous. Remember what we said? We said the difference between an ordinary point and a singular point is in this guy. The moment you divide through by it, and you put your value of x in this place, and you are getting a value that is equal to 0, then you know that it's a singular point. It's a singularity. That is what it means to be a singular point, right? It's a point in which the moment you put it into the function, that coefficient of y prime prime becomes 0. In extension, it means that the y prime prime itself will cease to exist, right? Because the moment this is 0, 0 times y prime prime will give you 0. So it will cease to exist. That's why it's a singular point. That is the point in which that differential equation ceases to be a second order differential equation. Now, we have two types of singular points. It's either a regular singular point or a irregular singular point. Now, what do we mean? Let's look at them in deep context. First off, we have this function. Remember, this is a fraction, Abi. This is another fraction. Let's bring these fractions to lowest terms. Lowest terms, complete lowest terms. Remember, so for instance, just think of it as if I'm saying 12 over 15 and bring it to lowest terms. If you are bringing this to lowest terms, you are getting 4 over 5. Abi? It is still a fraction, right? But it's in lowest terms. So it is that lowest terms. It is that lowest terms we want to work with now, and that is where we are going to generate the most amount of information. So let P of x be equal to B1 of x, or let me write it even better. That is P of x over x minus x naught raised to power m be equal to this in lowest terms. Abi? Let Q of x over x minus x naught raised to power n be equal to the second fraction, but this time also in lowest terms. That is, you have gotten out the ones that can divide themselves, the ones that you can factorize out, the ones that you can completely remove, and so on. You are left with the basic fraction that you can no longer cut. Then what are we having? We are having y prime prime plus P of x over x minus x naught raised to power m y prime plus Q of x over x minus x naught raised to power n y is equal to 0. Abi? Then if m is less or equal to 1 and n is less or equal to 2, then x equal to x naught is a regular singular point. That is, if the power of this denominator that is a coefficient of y prime is less or equal to 1, and if this one that is the coefficient of y is less or equal to 2, then it's a regular singular point. Another way you have to know it, or another way you need to know it, is that if you sum the power of the denominator and the power of the value of y, the answer you get must not be greater than 2. If you sum the power of the denominator and the power of the differential, the value you are getting must not be more than 2. So here, you are saying if it's less or equal to 1, that means you are saying like maximum 1 plus 1 is 2. You are good to go. Here, you would have what? Maximum 2. 2 plus 0. Because this is the base form. So it's like y is per 0. There is no differential on it. 2 plus 0 is 2. So once the maximum you can get when you sum them is 2, then it's a regular singular point. The moment you get something greater than 2, then you now have an irregular singular point. That is, if one of these two is not satisfied. Otherwise, so I'll just put otherwise. That means whether m is greater than 1 or n is greater than 2. One of the conditions might be satisfied, but the other one is not met. If at least one of them is not met, it is an irregular point. I hope that's clear. So sometimes it can be, we would face questions where we have to identify what kind of points we have, maybe in a list of points we are given. We are giving the singularities, you have to identify the singularities and then classify if it's a regular point or irregular point or whatever, and so on and so forth. So you see a lot of examples on that. That is not our core focus here. Our core focus now is to solve the differential equations that we want to evaluate at singular points. How do we now evaluate them at singular points? I hope we are together.
Williams wants to change over.
Oh yeah, no. Oh. You don't see William? Was it not the one that told you to come and change over? See how? Oh yeah. Let's continue. Okay. Now, the Frobenius method is a method for determining the solution at a regular singular point, right? The power series determines solution at an ordinary point. The Frobenius determines solution at a regular singular point. Now, there are basically different cases you can have for the Frobenius method. But first, let's start first and foremost with the general solution form. K starts from 0 to infinity, ak x is per k plus c. That is the biggest difference. X is per k plus c, right? That is the biggest difference between the Frobenius method and the power series. Of course, again, you know what this means. We are basically talking about evaluation at x equal to 0, right? X equal to 0. So if you extend beyond the concept of x equal to 0, then you know exactly what that will translate in. AK x minus x naught k plus c. Right? So that's a different ball game entirely, just like we saw for the power series case. But let's consider the origin case, yeah, at x equal to 0. Then we can go ahead to differentiate. But before we differentiate, let's consider what it looks like in basic form. So, okay, this place will continue. So here, when k is equal to 0, what will I have? I'll now have a naught x is per c. Unlike the power series where the x will disappear because it's just x is per 0. In this case, it's x is per 0 plus c. So the x won't disappear. You have plus a1 x is per 1 plus c, and so on and so forth. Which means by the time you differentiate this function, the very first value will never cancel out. And that's a very, very important key concept. The very first value, unlike the power series where the very first value is a constant, so if you differentiate the constant, it comes 0. Here, the very first value still has a variable. So if you differentiate it, it will still return back into the solution. So here, y prime will now be equal to what? So I'm using this to differentiate first and foremost. You have something like this plus c plus 1 e1 x is per c and so on and so forth. But in essential, what you are simply saying is that y prime is equal to summation k still is still at 0. Then you differentiate this k plus c ak x is per k plus c minus 1. So if you are doing y prime prime, that will simply be k starting from 0, k plus c minus 1, ak x is per k plus c minus 2. Basically, this is how the Frobenius method is going to work. So now, again, we have now introduced a new variable, which is c. We have introduced a new variable, which is c, which means we have to evaluate what that c is. Now, evaluating that c can be gotten from the auxiliary equation that will be generated inside the Frobenius series itself. However, how do we use that? How do we evaluate that series? How do we evaluate that Frobenius method? There are different cases for evaluation based on C, right? And these are the different cases for the Frobenius method. The first case tells you that if you subtract the two values, obviously, we would have two values. The reason why we always have two values is first and foremost, we are considering a differential equation in the second order. So even if we were to use the normal complementary solution that we normally do for complementing a particular solution, we will still be having m squared plus whatever. So we would have two solutions basically. That's not a problem. So we would have two values of C. If you subtract these two values and it is not giving you 0, but the subtraction is an integer. No, it's not an integer. That means you are subtracting it is not giving you 0, but that's not enough. The subtraction is not an integer. This will lead to the first case. We are going to look at an example on that. The second case, if you have equal roots, that's the second case. Third case, if C2 minus C1 is not equal to 0, but C2 or C1 minus C2, anywhere you like to put it, is in an integer. That is, this is the first case. Their subtraction is not 0, but their subtraction is not an integer. The second case, their subtraction is not 0, but their subtraction is an integer. But of course, this arrangement has a very, very important value. What does this mean? It means that you are saying that C1 has to be less than C2. Basically, C1 has to be less than C2. If you can do this, this will lead you to the third case. And then the fourth case for references. That is if C2 minus C1 is not 0 as well, but the subtraction is an integer. However, it is not strictly less. It is now less or equal to C2. So these are the four cases you can have. First case, the subtraction is not 0, but the subtraction is not an integer. That's the common case. Second case, they are equal. Third case, the subtraction is not 0, but it is an integer value that you get. And the first value of C is strictly less than the second value of C. Fourth case, the subtraction is not 0 still, but the subtraction is an integer. However, in this case, C1 is less or equal to C2. Less or equal to C2. So basically, this case is a very, very unique case, right? Because regardless of how you put it, if for any reason C1 is equal to C2, then you'll be back here, which would obviously give us a contradiction. And if C1 is less than C2, then we'll be back here. So usually we just consider the first three cases as our major focus. Essentially just the first case, sure. But we'll look at an example on those three cases for clarity. What's the time? So I expect, okay, we'll still go on for 1 more hour. So let's take case 1. So case 1, that is, we are saying C1 minus C2 is not 0, C1 minus C2 is not an integer. What we simply do in this case, when we have case like this, is we evaluate the Frobenius at both C1 and C2. This is going to be our final result. So if both of them are not the same thing, then evaluate at C1 first, then evaluate at C2 next. That is how we evaluate this first scenario. Okay, so let's continue. Let's take an example. Don't be long. Solve So this is our first question. Remember, the first goal is to make our substitutions for y. So let's y be equal to summation k starting from 0 to infinity ak x is per k plus c. Of course, we can verify if x equal to 0 is in fact a regular singular point. All you just have to do is, first off, put x equal to 0 here. Do you have 0? Obviously, you have 0. The next thing, use it to divide. If you use this function to divide, at x equal to 0, you would only have a value of a coefficient of a power 1 here. And then here you also have a power 1, which is less than 2, obviously. So it's obviously a regular singular point without issue. Okay. Another thing that might interest you to also note is the fact that x equal to minus 1 is in fact also a regular singular point. Right? X equal to minus 1 is also a regular singular point. So we can also evaluate this at x equal to minus 1. You can try that out if you like. Now, y prime will simply be k starting from 0 to infinity, k plus c, ak x is per k plus c minus 1. Then y prime prime is equal to summation k starting from 0 to infinity, k plus c minus 1, ak x is per k plus c minus 2. Right? The next step is now to bring all of this and substitute it into this formula. So, what we have, let's expand this first and foremost. We now have 2x squared plus 2x, all of them into summation k starting from 0 to infinity, k plus c, k plus c minus 1, ak x is per k plus c minus 2, and then here you'd have plus 3x plus 3, summation k starting from 0 to infinity, k plus c, ak x k plus c minus 1, and then lastly minus summation k starting from 0 to infinity, ak x k plus c. I hope we are together. The next thing from here is to expand this function. So 2x squared multiplied by this. Remember, we are still going to operate on the rules of powers, indices. K starting from 0 to infinity, k plus c minus 1, ak x raised to power k, plus c, right? Because 2 minus 2 will give us 0. I think we are missing something. We are missing a 2 here, right? X squared and this one, in this to apply, we have this one left. 2 times the summation is this. Then in the second one, would have plus 2. Would this place contain it? Nope. Let's put it down. Plus 2 summation, k starting from 0 to infinity, k plus c minus 1, ak x is per k plus c minus 1. And then down here we expand, plus 3 summation, k equal to 0 to infinity, k plus c, ak x k plus c, then plus c, k starting from 0 to infinity, k plus c, ak x k plus c minus 1, and then minus summation, k starting from 0 to infinity, ak x k plus c is equal to 0. So this is the first step. This is the expansion step. What we'll now do after this is to then simplify just as we did before. So So far, I hope we are all clear as to where we have gotten to, right? Please don't get lost. That's going to be like the most crucial point we are going to have. Next, unlike the power series solution, where the counters were different because of how we differentiated, we had some k equal to 1, k equal to 2, and so on. It was easy for us to unify the variable in that sense. However, for this one, it is a very, very different scenario. All the counters are the same thing from the first place. All the counters are the same. So how then can we then unify the variables, which are obviously not the same? Here you have k plus c, but here you have k plus c minus 1. Here you have k plus c minus 1. Here you have k plus c, k plus c. You need to bring all of them to k plus c. But unlike before where you could easily play around with your counter, here you don't have that kind of freedom. So what do? First thing is you will give yourself room to play with that counter. We have no problem with this first one. The counter is fine, the variable is fine. So we write it out. I can probably bring the 2 inside, so I won't forget it on the way. 2 into k plus c minus 1, ak x k plus c. Here, what do? I need to be able to remove this. Now, remember, when we were dealing with the variables in power series, in this case, what we need is k plus c. Someone send a message in chat. Oh, okay. Here, in the power series scenario, if we had a scenario like this in the variable, what we did is add 1 here and subtract 1 from the counter, Abi? But if we go ahead to do that immediately here, we would have a problem. Why would we have a problem? Because if we add 1 to this power, by the time we want to subtract here, we would have a negative because it's already 0. So 0 minus 1 will give us minus 1. We would have a negative counter, which would not make so much sense. So since what we want to add is 1, why don't we split this counter so that the counter is now starting from k equal to 1? So that by the time we add 1 to the power and we subtract 1 from k equal to 1, we will be back at k equal to 0. Does that make a lot of sense? Let's see what I'm saying. In this case now, we have k plus c minus 1. So I'll shift this, I'll pull 1 or split out 1 from this counter. So when k is equal to 0, what happens? I'll have plus 2. When k is equal to 0, this will be c. This will be c minus 1. This will be a naught. And this will be what? K equal to 0. So that will be x raised to power c minus 1. Right? And the moment I brought down k equal to 0, what would now be left? I will now be left with plus k equal to 1 to infinity. Then bring the 2 inside. 2 into k plus c. K plus c minus 1. ak x k plus c minus 1. What is this simple thing telling me? What this will show me immediately is by the time I now add 1 here, I can now easily subtract 1 here and balance everything up. So that is the reason why I splitted out that value. Please take note of that important part. Here I have no problem. I have 0, I have k plus c. So I'll just bring it back. Plus 3 summation k starting from 0 to infinity. K plus c, akx k plus c. But here I will also do the same thing. When k is equal to 0, I'll bring it out. I'll have plus 3c a naught x is per c minus 1. And then when k is equal to 1, what will I have? Plus summation k starting from 1 to infinity. 3k plus c ak x is per k plus c minus 1. Very good. And then here, I'll still have the same thing because that is stable. K starting from 0 to infinity. ak x k plus c. And none of this will be equal to 0. Now, I can now shift these counters easily. That's the first step. So the first step here was to create an avenue for me to shift. Now that I've created that avenue, I can now shift these ones. Remember, anywhere I see k, I must do exactly what the function is. If I added 1 to the function, I add it all across the function. And then I do the reverse of the counter. That is how the process works. So there is no such thing as a bias situation. You have to do every single thing across board. Now, the next thing to also look at is you have this one and you have this one. Let's see if you can collect like terms. Here you'd have 2c squared minus 2c. And here you have plus 3c. By the time you bring them all together, what will we have? 2c squared plus c. 2c squared plus c. Right? So the reason why we can bring them together is because of what this coefficient is. This is a naught x is per c minus 1. This is also a naught x is per c minus 1. So bringing them all together in that form has absolutely no offense. And that's exactly what I'm going to do in the next step. So I will now have summation k starting from 0 to infinity, 2k plus c minus 1, ak x is per k plus c. And then here I'll be left with what? 2c squared plus c, a naught x is per c minus 1. Here I'll be left with plus summation k starting from 0 because 1 minus 1 is 0, 2k plus c plus 1, k plus c minus 1 plus 1 is 0, ak plus 1, x is per k plus c. Here we'll have plus 3 summation k starting from 0 to infinity, k plus c, ak x is per k plus c. And then finally, we'd have plus summation k starting from 0 to infinity, 3 into k plus c plus 1, a k plus 1, x raised to power k plus c, and then okay. Alright, we are good. And then here we have minus summation k starting from 0 to infinity ak x is power k plus c. All of it is equal to 0. So, as I've always said, the biggest problem you would have as far as this method is concerned is in the computation. The computations are always very, very large. So, if you lose your bearings a little, you might have some problems catching back up. Now, here we have these values of k plus 1, and then we have the rest for ak. So let's collect the terms that are obviously close together, and then let's leave out the rest. So here we would have 2c squared plus c a naught x raised to power c minus 1, and then plus summation k starting from 0 to infinity, and then the entire load. So here, let's bring the ak plus 1 together first and foremost. Now, in these two, you are supposed to add this and this together. K plus c is common, abi k plus c plus 1 is common. And then by the time you bring it, what would you have left? 2 k plus c plus 3. Right? And then here, you'd have ak plus 1. And then on the ak side, that's on this side, what would we have? Remember, we are now bringing this one, and then this one, which is also minus 1, together, right? So let's see. K plus c is common in these two, plus k plus c into 2k plus c minus 1, and then this one plus 3, this is the first part, and then minus 1. All of this multiplied by ak, and all of this multiplied by x raised to power k plus c, and all of this is equal to 0. So this is where we are at. Let's make sure we did not leave any coefficients hanging. K plus c plus 1 is common here. When you remove it out here, you have 2k plus c plus 3. Here you have k plus c common. So you have 2 into k plus c minus 1 plus 3. Right? And then you have here minus 1, which is the last value. We are good. The most important thing is ensuring that we don't misplace our values. Now, of course, we can go one more round before we now begin our search for what c is and so on and so forth. So here we have 2c squared plus c a naught x raised to power c minus 1. And then in this place we have plus summation k starting from 0 to infinity. This one will now be k plus c plus 1, 2k plus 2c plus 3, ak plus 1, and then this one will now be, of course, you can either decide to leave it that way, or you can decide to multiply. Either one you decide to use is fine. Here, but I can open this and then add it to this. This will now be k plus c, 2k plus 2c minus 2 plus 3. This will give me 2k plus 2c plus 1 minus 1 ak x raised to power k plus c is equal to 0. And with that, we have gotten the very first stage of our answer. This is the very, very important part. Now, the next thing for us to do is to evaluate what C is. At this point, I hope it is clear. Now, see this first one. It is this first equation that we will use to generate what in fact our values of C would be. At x equal to x raised power C minus 1, we would have 2C squared plus C A naught to be equal to 0, right? It's essentially the same thing as saying that 2C squared plus C is equal to 0, because if you divide both sides by A naught, you would have 0, provided, of course, A naught is not equal to 0. So, or you can say, or A naught is equal to 0. Anyone you like, but this is exactly where your focus should be on. Now, for this one, if I factorize, I'll have 2C plus 1 is equal to 0. So that means that C is equal to 0 or C is equal to minus 1 over 2. That's simple factorization. So I've gotten my C and C1 and C2, right? Clearly, C1 minus C2 is not equal to 0. And more importantly, C1 minus C2 is not an integer. So that is the condition for the first case. So you see that we have to complete, or first and foremost, have solved the Frobenius series to a great extent before we even start talking about the methods or the cases itself. So the cases are not something we need to worry about. So let's just assume this is not possible. So this can be equal to 0, right? So let's just leave the A naught part out of it. Now, okay. Oh yeah. Now, we are at this second part. Remember what the first case is saying. If this is satisfied, they are not equal to 0 and they are not equal to integers, or they are not integers. You evaluate both of them via the Frobenius method. So let's use the first one. For this one, at C1 is equal to 0, what happens? Anywhere you see C here, make it equal to 0. So what do we have? Let's use x. This is x raised power k plus C, abi? So that becomes x raised power k. And what will be the coefficient? All of this. This place will now become k plus 1. This place will become what? 2k plus 3. This one is still ak plus 1. Here will now become plus k into 2k plus 1, abi, minus 1, all of it into what? AK. And of course, this is equal to 0. This is going to be like the very first step we take. Now, the next thing is, alright, let's now make AK plus 1 solve the formula. So we are saying that AK plus 1 AK plus 1 is now equal to this minus k 2k plus 1 minus 1 divided by what? K plus 1 2k plus 3 AK. And of course, k in this case is starting from, remember where the counter is starting from 0. So k is greater than or equal to 0. Simple and straightforward. So essentially for this one, A naught will simply be the only recurring value. And that follows because even in the first equation we picked that generated the values of C, A naught was still the recurring value as well. So that solves that part of the business. Michael, you are raising your hand. What's up? Is anything up, Michael? Okay, I'll assume there's no issues. So let's continue. Now, of course, remember if you multiply all through by minus, this is the same thing as writing AK plus 1 is equal to 1 minus K into 2K plus 1 divided by K plus 1, 2K plus 3, AK. So anyhow you decide to write it is fine. That's your own discretion to decide with. Now, when K is equal to 0, so let's start generating our values. When K is equal to 0, what do we have? We have A1, K equal to 0 here. You have 1 divided by, all of this is 0. This is 0, this will be 1 multiplied by what? 3, A naught. When K is equal to 1, what happens? You have A2, this is 1, this is 1, this is 2 plus 1, that's 3, Abi? So this will now be 1 minus 1 into 3 divided by what? 2 times 5, right? A1, and this will simply be equal to minus 2 divided by 2 times 5, A1, right? But don't forget, A1 itself is all of this. So you have it as minus 2 over 2.5 multiplied by what? 1 over 1.3 A naught. So if you put all of these values together, what do you have? Minus 1, so let's cancel the 2, divided by 135 A naught, right? 135 A naught. Let's continue. We can generate more. So now at this point, what we are trying to do is formulate a pattern. So it's easy for us to generalize, right? But usually, if for any reason you can't generalize and it's giving you difficulty to generalize, there's no point. Or how would I put it? There's no reason for you to go so far. If you're able to get to this point, and it is a generalization you cannot do, just return all of this into the Frobenius series and write it out in full like that. So that's A naught plus 1 over 1 times 3 A naught x plus 1 over 1 times 3 times 5. No need for you to generalize. There's no point to kill yourself to that extent. But if you're able to generalize, then fine. So here, K equals to 3, we have A3. In this case, we now have 1 minus, that will be 2 into 5 divided by what? Divided by 3 times 7, right? This is A2. And in this case, you now have 1 minus 10, that's minus 9, divided by 3 times 7, multiplied by A2 is obviously 1, minus 1, sorry, but by 135 A naught. So now we want to create a pattern. How do we create that pattern? Of course, we have started with 135. So next up we can have 1357, right? So 3 cancels here, we have 3 left. You now have 1 minus times minus plus. You now have 3 divided by 1357 A naught. So we have a pattern. Whether you like it or not, there is a pattern. We can maintain a pattern for the numerator as well. there's also a very large possibility that the numerator might follow a pattern of an odd number as well. Let's see. So sometimes I just generate the functions or the variables, and if I'm not able to sum it, I just leave it like that. 3 into 2 times 3 is 6, 7, divided by what? 4 times 3, 6, 9. This is 8, 3. This will now be 3 times 7 is 21. This will now be minus 20 divided by 4 times 9 times 3 divided by what? 1, 3, 5, 7, A naught. And what do you notice? You have 1, 3, 5, 7, 9. 4 cancels here, you have 5. So what do you have? Minus 3 times 5 divided by 1, 3, 5, 7, 9, A naught. So I feel there's a pattern. What is the first pattern? The sign is alternating. The second pattern is the fact that we have gone from 1 to 3. So we can even rewrite this as 1.3. Can write this one as 1.3.5 and so on and so forth. So the next one should be 1.3.5.7. That is another pattern that we have generated. Now let's try to rewrite this minus sign that is moving on. We started from a positive to a negative. So you can say this is minus 1 raised to power 0. This is minus 1 raised to power 1. This is minus 1. This is minus 1 raised to power 2. And this is going to be minus 1 raised to power 3. Something like this. And it continues. So it means that AK right, or AK plus 1 in this case, because AK plus 1 is what we are generating. Let's start with AK plus 1 will simply be what? Minus 1 raised to power K, Abi, 1.3.5. However it likes. And what is the pattern of formation of this? When you are at K equal to 0, you have 1. When you have K equal to 1, you still have 1. When you are at K equal to 2, you have 1 and 3. So there is a pattern. You can simply use 2. What do we want to use? You can probably use 2K plus 1 if it works. So when K is equal to 0, you'd have 1. When K is equal to 1, you'd have 3. But we don't want that, so probably let's just use K minus 1. And so on and so forth. Divided by, here you have 1.3.7.5.7.9, and you have another pattern being generated. So you can sum that exactly how the growth is. You can probably use 2K plus 3 or something. So this is just me trying to randomly generate these patterns. Of course, if you take your time to generate it, you should have something different. Or let's generate everything in terms of AK. So this will be AK plus 1. Let's use AK plus 1. So we have A1, okay, let's use this. A1, A2, A3, A4, A5. My mind is telling me that the pattern is not completely clear, but regardless, we can evaluate it like this. And if for any reason you feel like this pattern might be too complex, you can also still generate another pattern based on values with which you can cancel out. So for instance, here you have 1.3.5. Let's say you don't want to use the 1 itself. Let's say you want to use 3.5. Let's see if that will simplify our life. By the time we get here, the 3 can also cancel. We'll be left with 5.7. Okay, let's see if this works. We left with 5.7. By the time we come here, this is 1, Abby, 5.7. So here, what happens? 5 will cancel. We'll be left with 7.9. Okay. So I think this is easier. Minus 1 raised to power 3. Abby? Okay, this is easier. So if we are generating the sequence this way, I don't think I will have any reason to stress my brain. This will simply just be minus 1 raised to power k minus 1. Abby? All divided by these ones. So this will simply be, when you have 4, you have 2 raised to power 4, you have 2k minus 1. And then here you have 2k plus 1. K starting from 1. And then this will be ak minus 1. Okay, so this should be valid. So when k is equal to 0, we have the normal case. When k is equal to 1, which is this one, let's test it. That will be 1 minus 1, you would have positive. 1 minus 1, you have a naught. 2 into 1 minus 1 is 1. 2 into 1 plus 1 is 3. Okay, that works. When k is equal to 2, does it work? 2 minus 1, you have minus 1. Okay, then 2 into 2 minus 1 is 3. 2 into 2 plus 1 is 5. Okay, so that's good. So this is a recurrence formula that holds true for this Frobenius series. Do not forget, this is just for C1 is equal to 0. So that's essentially the reason why I don't really stress much. As far as if it's an exam situation. Can you hear me? Can you hear me now? Okay. When you stopped the talk before? All right, so this is just for C1 is equal to 0. And that's why I don't really waste so much time saying I'm trying to solve, because the bulk of our work is still so large. So if you waste so much time trying to think of how to form the recurrence, you might waste too much time, basically. You might waste too much time. So the point is just for you to keep moving on. Essentially, we will have to form a Frobenius series for when C0 or C1 is equal to 0. So that's something we have to always do. So here we have gotten AK and we have generalized. Remember that y is equal to summation k starting from 0 to infinity AK x raised to k plus c. Abi? So in this case we are at C1 equal to 0. So anywhere we see c, it is now 0, right? So here our function now becomes a naught x raised to 0 plus a1 x raised to 1 plus a2 x raised to 2 plus a3 x raised to 3 plus ... Right? Because here the C1 value we used is 0. Always keep that in mind. So by the time we now put that in here, we now have a naught plus a1 is that guy, a2 is that guy. Now, instead of writing all this sequence, I can now replace it in general by this term. I will now say plus summation k starting from 1 to infinity, because that's the counter, minus 1 raised to power k minus 1 divided by 2k minus 1, 2k plus 1, x raised to power what? K. This will now be my final answer. So this is why we generalize, so that we are able to now put it in summation. So when we put k equal to 1, I'll get that guy, plus k equal to 2, I'll get this guy, plus, k equal to 1, I'll get this one, k equal to 2, I'll get this one, k equal to 3, I'll get this one, and so on and so forth. So that is essentially why we put, that's essentially why we generate all these terms that we have. But you always have to keep all of this in mind. This one should not even be k minus 1. This is a naught. A naught, because all of them end with a naught. So all of them is in terms of a naught. Of course, you can still go ahead to say you want to factorize this and this and bring a naught out. That's fine. Anyone you decide to use is good. Now, for the second step, at C2 equal to minus 1 over 2. I don't think I want to do this so that we'll be able to have time to do the other method. But basically, what would we do? We will come back to this sum, and then everywhere we see C, we will replace it by minus 1 over 2. And then we will generate or attempt to generate A1, A2, A3 for it. And then we will go forward to find this summation or recurrence if we can, and then write it in its Frobenius series form. So let me just ask now, should we still go ahead to do this C2, or is something we can do on our own so that we can move to another case? So what do you think? Is this something you can do, or should we do it together and then you would move on to the next case? Okay, so I should just write out what the final result would be, right, Abi? Okay, so, God have mercy. All right. So we have gotten this one for a naught. Remember I said that you can factorize, what do you call it? You can factorize a naught that is common here and bring all of them together if you like. That is your own choice to make. And even if you do that, you would simply be saving yourself a lot of stress, right? Because what you are just going to be having is a naught into 1 plus summation k starting from 1 to infinity minus 1 raised to power k minus 1, Abi? A naught no, so there will be no a naught here. Divided by 2k minus 1, 2k plus 1, x raised to power k, right? So this is us bringing them all together. One thing that you should also note is that if you have this term, it is easy for you to put this one into this sum. It is easy for you to put this one into this sum. How? This is your sum value. If k is equal to 0 for this value, what happens? That is, if for instance we want to shift it. If k is equal to 0, if we want to shift this to start from k equal to 0, what will happen? We would have essentially that minus 1 raised to power k minus 1 divided by 2k minus 1, 2k plus 1. Here, for it to be able to obtain 1, when k is equal to 0, what will we have? We'll have minus 1 raised to power 0 minus 1 divided by minus 1 times 1, Abi? Which means essentially that if we want to rewrite this one into this summation, it suffices for us to be able to start this counter, this alternate counter from the previous alternate version. So if this one is starting from minus 1 raised to power k minus 1, what if we started from minus 1 raised to power k plus 1? What happens if we start that counter that way? Let's see. if you consider minus 1 raised to power k plus 1 divided by 2k minus 1, 2k plus 1, what happens? In that regard, you now have minus 1 raised to power 0 plus 1 divided by minus 1 dot 1. This one will give us minus 1 raised divided by minus 1. And by extension, what would we have? You would have 1. But it would not change your entire function. So by the time you get to when k is equal to 1, you will still be fine. Because when k is equal to 1, you will be back to this, you'll be back to obtaining A1, right? You'll be back to obtaining A1. And A1 will now be 1 plus 1 in that regard. So it will be positive. 1 plus 1 is possible. Unlike this one where it is 1 minus 1, which is giving us 0. Now you'll be having 1 plus 1. So it means that I can write all of this. So this is just a 3 to bring it together. Now the reason why we are bringing it together is so that we have a general final answer is equal to, in this case, we now have A naught into summation k starting from 0 to infinity now, so that we'll be able to bring this 1 in, minus 1 raised to power k plus 1 divided by 2k minus 1, 2k plus 1, x raised to power k. And of course, when k is equal to 0, you'd have that guy, right? Now, remember this is just for C1 equal to 0. So let's just stamp this Y1. At C2 equal to minus half, you will follow the entire pattern. So I'll just write the final answer so you can verify that. In that regard, you would also get Y2. Funny enough, it is even shorter, actually. But then if you follow the process, you will get that the only thing you would have is A naught x raised to power minus half plus A1 x raised to power half, which is something you can write as A naught x raised to power minus half plus x raised to power half. This is just what you are going to have, which means that the only term that will exist is just A naught and A1. And A1 is in fact equal to A naught. By the time you solve it, you get exactly how that happens. Now, to now get the final result, y will now be equal to y1 plus y2. Think of it as if when we are doing your normal differential, you are doing y is equal to yc plus yp, which is complementary plus particular. We are using the same pattern. So here, we will now add this one to this one. But because we know that A naught here is not the same thing as this A naught, right? We will denote it by a new letter. So that will now be A into summation k starting from 0 to infinity minus 1 raised to power k plus 1 divided by 2k minus 1, 2k plus 1, x raised to power k plus b x raised to power minus half plus x raised to power half. And this will now be our final result. So writing this final result is now proof that we have solved completely this Frobenius series, right? So in this case where the subtraction is not 0 and is not an integer, you solve for the two c's, you get their separate Frobenius series, then you add the two series together, right? Where you are still denoting and maintaining the uniqueness of their coefficients, right? That will now be your final results, and that will be all. I hope that's clear. Oh yeah, so let's, God have mercy. Okay, so let's time thing. Let's quickly rush to method 2. Let's rush to method 2, right? And then I'll just give you a brief overview of what method 2 is all about. So usually it's usually method 1 that is so common, but we should not underestimate anything. So let's at least make sure we cover as much as possible. I'm supposed to have another meeting now, so in like 30 minutes we would round up, or like 20 minutes. So case 2 now. What's case 2? That is if C1 is equal to C2. So we have equal roots. So how do we solve them? When we have equal roots, what we do essentially is that we will evaluate the Frobenius series at C, which is obviously just 1C, right? We evaluate the Frobenius series at that 1C. And then when we have that Frobenius series and we have gotten it, what we will now do essentially is we will now differentiate it. So this one at C, we will now differentiate it to get del Y del C. And we'll now evaluate this one too at C. So we evaluate Y at C. We also now evaluate del Y del C at C. That's partial differential at C. That is not how we generate the two results. So how that one will work, we will now see exactly what we are saying. Let's go to work. Solve x squared y. Obviously, x equal to 0 is also a regular singular point here. We can verify that. If y is equal to summation k starting from 0 to infinity, ak x raised by k plus c, y prime is equal to summation k starting from 0 to infinity, k plus c, ak x k plus c minus 1. And then you have y prime prime, which is equal to summation k starting from 0 to infinity, k plus c minus 1, ak x k plus c minus 2. So we'll take all of these three and then substitute into the formula, as always. We'll connect it. Okay. Oh yeah, let's go. Oh yeah, now let's put it inside. We'll now have x squared summation k starting from 0 to infinity, k plus c minus 1, ak x k plus c minus 2. Then minus x summation k starting from 0 to infinity. Nope. Minus x into 1 plus x. So let's probably just expand it. Minus x plus x squared summation k starting from 0 to infinity, k plus c, ak x k plus c minus 1. Then plus summation k starting from 0 to infinity, ak x k plus c is equal to 0. So I feel like all these points you should be getting the hang of all this part of the concept already. So here we'll now have summation k starting from 0 to infinity, k plus c minus 1, ak x k plus c. Here we have minus summation k starting from 0 to infinity. This one is the first one I'm using to multiply. So I have k plus c, ak x k plus c, and then this second one. Now I have minus summation k starting from 0 to infinity, k plus c, ak x k plus c plus 1. Wahala. Then plus summation k starting from 0 to infinity, ak x k plus c is equal to 0. Right? So we have this. The next thing for us to now do is to now, of course, unify the counters where we can, and then play around with the ones we cannot. So basically, the only one that is giving us issue is this guy. But we don't have a problem. Why? Because here, we don't even have to, where's my blue marker? We don't even have to do so much. We can simply just shift, right? Because here, we want it to come back to k plus c, and it's k plus c plus 1, abi? So we can subtract 1 here and add 1 here, and we are good. Sticky. So here we subtract 1, subtract 1. So we don't even need to give ourselves so much headache as saying we are doing one major pulling out like the other one. So here we will now have summation k starting from 0 to infinity. In this case, this will now be k plus c minus 1, akx k plus c, minus summation k starting from 0 to infinity. We are good with this one as well. K plus c, akx k plus c. But that one will now become minus summation k starting from 1 to infinity, k plus c, akx k plus c. No, this will be k minus 1. Haha. K plus c minus 1, ak minus 1, x k plus c, plus summation k starting from 0 to infinity, ak x k plus c, and this will be equal to 0. So this is how we have shifted it. So you see now we have unified the variable. The only thing we now have to work out for, which is now the biggest problem, is, remember, once you have unified the variable, if the counters are not unified, you now have to push or pull out the counters till they get to k equal to 1. So that's the next step we are doing. I'm sure we are already getting very, very familiar with how the entire process is working. So now when k is equal to 0 here, what happens? I'll have c into c minus 1, a naught x raised to power c. Then here, of course, here I'll be left with k equal to 1 to infinity, k plus c minus 1, ak x is per k plus c. When k equal to 0 here, I have minus c, a naught x is per c. Then, of course, minus summation k starting from 1 to infinity, k plus c, ak x k plus c. And then here, I'm fine with it because obviously now the way we cause wahala with this. So we have k equal to 1 to infinity, k plus c minus 1, ak minus 1, x k plus c. But here I have to bring out 1 as well when k is equal to 0. So I have plus a naught x is per c plus summation k starting from 0 to infinity, ak x is per k plus c is equal to 0. So we are there. Now, how do we proceed? We bring all these ones together, this one and this guy. Abi? We bring it all together. What we have? This is c squared minus c. This will now become minus 2c plus 1. So we can have c squared minus 2c plus 1. A naught x is per c. And then the sums now. We have ak. In fact, all of them are so good except this guy. Right? So I have plus summation k starting from 1 to infinity. So I bring all the ak's together first. So I have this one, and this one. K plus C is common here, so I have K plus C. Then I have K plus C minus 1, right? K plus C, factorize K plus C out, factorize K plus C out. And then here, you'd have plus 1, and all of this will multiply AK, right? So we have dealt with this, this, and this. Remember, keeping track of the equations is like the hardest part in this entire space. Minus K plus C minus 1, AK minus 1, all of it xk plus C is equal to 0. Good. Now, this first equation, which is x raised power C, if you consider it if A naught is not 0, what happens? You will have C squared minus 2C plus 1 is equal to 0. Obviously, this is C minus 1 all squared. Obviously, this is telling you that C is equal to 1 twice, which is why we have that case. Now, how do we evaluate it? For this one, we don't rush into the evaluation at this point. We will first have, since of course we know that C equal to 1 is the value, it's equal roots. Unlike this one where we started substituting it, we have cleaned it. Unlike this one where we started substituting it into the sum, here we will get the recurrence first before we now bring in the value of C, because they are obviously the same value. So that is the only way we are ensuring that yes, we don't repeat the process. So how do we do that? Let's see. So here, remember, we have dealt with the upper part. So we are now dealing with the lower part, basically. So when x raised by k plus c is what we have, we'll now have k plus c minus 2 plus 1, all of this multiplying ak, then minus k plus c minus 1, ak minus 1, all of this has to be equal to 0. Very good. Which means that ak is equal to k plus c minus 1, all divided by what? K plus c minus 2 plus 1 ak minus 1. And of course, the counter is starting from when k is greater than or equal to 1. Very good. So we have obtained that value first and foremost. Now, we can go further. Interesting. How do I find the easiest way to explain this? Now, okay, the very easiest thing or the biggest thing we can do is if we can simplify this denominator. Now, it is not a general reason. It's not a major reason. It's not a goal per se. If you can evaluate your values of k's, that means your A1, your A2, your A3, your A4, like this, and you are able to also generate a pattern for it, it's fine. The reason why I went so far as to split it out is because generating the pattern like this proved so difficult for me. But in an exam situation, I already will put in mind that not every single person might have the opportunity to think outside the box and say, okay, let's rewrite the summation. Now, the biggest logic that made me write the summation is this. We have this counter as ak minus 1. I don't want a counter that is negative. So if I can influence this counter such that it becomes a positive counter, it's easier for me to deal with. Now, how do I influence this counter to become positive? The same rule still applies, just as we did it when we work on the summations and we say that the function, whatever you do to the function, you reverse it in the counter. In this case, whatever you do to the function, you reverse it in this counter here. So it means that I can write this whole thing as, here, I want, this is k minus 1. This is k minus 1 here. I want to move it. I want to make it positive, which means the closest possible thing I can have is ak. So it means that I have to add 1 here. Now on this side, anywhere I see k, I will add 1 to it. And here, I will subtract 1. Simple and straightforward. Just as I do it in the sums, I can do it here as well. If I want to swap or if I want to move the counter totally, and it's this kind of subscript that I want to change, it was different, and it is completely different to the case where we changed the power on the alternating series, which we did in the previous Frobenius method. In that one, it is just the alternating series that we have to change. And the reason why we can change the alternating series alone is because it can only have 2 values, minus 1 and 1. So even if we alter the power, so long as we are still generating the values of minus 1 and 1, it will make a lot of difference, right? Unlike this one, there's no alternating series. So whatever we make that we affect one part of this function must affect all of it. So if you are affecting the entire function positively, then the counter will have the reverse, which is the negative value. Which means all of this will now become ak plus 1 is equal to, this one will now become k plus c divided by what? K plus c plus 1, k plus c minus 1 plus 1 ak. Now you ask yourself that how does this make it easy? It does, because this bracket now is now a difference of 2 squares, which means I can now write it as k plus c divided by k plus c squared minus 1 plus 1 ak, which means I can now write it as what? Ak plus 1 is equal to k plus c divided by what? This will cancel, k plus c squared ak. And of course, k is now going to start from 0 because of this counter, which means that I now have ak plus 1 to be equal to what? Ak over what? K plus c, k starting from 0. Basically. So you see exactly how simple my life is. I could have continued operating on this one, but then the moment I shifted counters, it became so simple. So sometimes shifting the counters become a blessing in disguise. Now, notice that we have still not put in the values of c. We are not going to put the values of c into it until we form that recurrence. That is one major thing you have to take note of as far as this second method is concerned. So now let's start from our recurrence. When k is equal to 0, what do we have? We have a1, and this will now be a0 over c. When k is equal to 1, we have a2, and that will be a1 over c plus 1, which is what? a0 over c plus 1 times c. When k is equal to 2, what happens? We have a3, which is what? a2 over c plus 2. And this will be what? a0 over c plus 1, no, c plus 2, c plus 1, c. Right? And so on and so forth. The pattern continues. The pattern continues. Now, if, of course, at this point, I feel like we should have gotten very, very close and very, very familiar with the concept of factorial functions already. We have an exam to prepare for. Factorial functions will tell us that so long as this continues infinitely, this is in fact a factorial function on an infinite scale, right? If it was continuing to n, there will now be Cn, as we normally write it. But here, we are not going to use the factorial function because it's assumed that when you are dealing with Frobenius, you have not yet done factorial. So even if factorial function comes to your mind in the exam, you are not compelled to use it. In fact, I will advise you not to use it. It works, yes, you can use it, but if you have no reason to do so, you don't need to. So here, it means that at this point, what do I have? I can generalize that my AK, right, for all k, is in fact going to be what? A0 divided by what? C, c plus 1, c plus 2, and I'll continue to multiply it till I get to what? C plus k minus 1. right? C plus k minus 1. The bracket is not complete. Right? And then you can check for all k. You can check if this is correct. Of course, I'm starting my k starting from 1, right? To reference it. And you can check. When k is equal to 3, you have A3, abi? 3 minus 1, 2, C plus 2. Basically, that's how you do your counting. So we can generalize on that form. And if you don't like to use this, you can also remember, if you want to switch it back, if you want to start it from AK plus 1, just add 1 all this way, subtract 1 here. That's fine. So here you now have AK plus 1. Would that be equal to A0 divided by C? C plus 1, C plus 2, C plus K. K starting from 0. So anyone you decide to use is fine. That is very, very good. We have generalized. By extension, our Frobenius series is equal to what? Summation k starting from 0 to infinity, ak x raised to power k plus c. This will now be what? A0 x raised to power c plus a1 x raised to power 1 plus c plus a2 x raised to power 2 plus c, and so on and so forth. Right? So we can generalize this. Remember, this is starting the counter from 0. So this will now be A0 x raised to power c plus summation k starting from 0 to infinity, A0 divided by c into c plus 1, c plus 2, c plus k, and then remember x raised to power k plus c. But in this case, remember, k starts from 1 and you're representing these guys. So you can probably just use x raised to power k plus c plus 1. So you have that. And that's why, personally, I prefer writing it in this form. Because if I write it in this form, I can start my counter from k equal to 1 safely, and x is per k plus c without problem. So anyhow you decide to write it is fine. That is yours to think of. Now, we can now combine. If you want to write it here, we have written it this way. If you decide to write it this form, let me write it out for you. Or y is equal to A0 x raised per c plus summation k starting from 1 now to infinity, A0 c into c plus 1, c plus 2, c plus k minus 1, x raised to power k plus c. Anyone you decide to write is fine. Both of them are totally correct. There is no problem about it. Good. Now, let's now finally substitute the value of c into it. But before we now substitute it, we can now state the most important thing. So when the method said if you have two equal roots, you evaluate the first one at c, that is, evaluate y at c, then evaluate the y del c at c as well. This is evaluating y. This is y. So at this point, all you just have to do is put the value of c into it. Then this function that you have, differentiate it with respect to c. Then put in the value of c. The textbook was so smart not to do it. So here at c equal to 1, the value of y will now be equal to what? A0 x plus summation k starting from 1 to infinity. I'm using the bottom one. A0 into 1, 1 plus 1, 1 plus 2, and what would I have at the end? K, abi? Because I have 1 plus k minus 1, that's k. Abi? X raised to power k plus 1. And what does this mean? I'll have A0 x plus summation k starting from 1 to infinity, A0 over k factorial, because this is k factorial, x raised power k plus 1. Straightforward. So that is me evaluating at c equal to 1. To now get the second, so this is obviously y1 now. So now get the second series, and I have to partially differentiate this one. I have to partially differentiate this one with respect to c. I kid you not, I won't be differentiating that. I can easily differentiate this. This will be ca dot x raised power c minus 1. But this place, I would not be differentiating it because this is a product of functions of c, and they are still in reciprocal form. So it's obviously a quotient rule. How you want to carry out the quotient rule, that I will leave to your imagination. But to get the second result, you have to differentiate this value of y with respect to c. Then after I've gotten the y del c, you now put c equal to 1 into it to generate the second result. That's why I said usually, as far as the system has gone, there's always a lot of emphasis more on questions about the first method, right? Because of the complications in solving beyond a lot of steps for the other methods or cases, right? But it won't hurt to keep those methods in mind. So we couldn't cover so much, but we covered so much as well. We have looked at the power series and the Frobenius method. And at least we have gotten these two topics out of the way. Probably we'll just walk around solving some questions about the other methods and the other topics, so we can keep ourselves fresh about it, right? All right, we have had a lovely run. That's all we have for class. Is there any question, basically?